everybody, it's Mr. Mullicash again. In previous videos I had a little bit of an audio issue and I'm using a different microphone and it may sound like I'm in a can. Sorry about that, but I'm back. Welcome back to another fun-filled video of Calculus 1, and I appreciate you hanging in there with me. This video is going to have a lot of content in it. I mean a lot. We're going to talk about left and right midpoint sums, Riemann sums, definite integral assigned area, and what I mean by SIGNED is positive or negative, the indefinite integral using antiderivatives, and the fundamental theorem of calculus. And let's go ahead and jump right into a graph that I've graphed on Desmos calculator. And so it's the graph of x squared from -1 to 4. And remember from last week's video that the idea is these days in calculus is to find how much area there is between this graph and the x-axis. So I can sort of cover all that. I can make my marker a little bit bigger, and I can try to cover all this area. But the question is like, how much area is there here, right? What is the area of all this? And if it were a triangle, if it were something like a triangle, it would be pretty easy to find, right? You could use 1/2 base times height. It's not quite a triangle, is it? You could use triangles to approximate the area. And that sort of thing. If it were a circle, we could find the area. If it were a polygon, like a square or rectangle, we could find the area. So what is usually done in situations like this is what we try to do is to split up the interval from -1 to 4 into what are called subintervals. And so I'll use 5 subintervals to make it convenient. So the first subinterval will start at -1 and stop at 0. And then we'll make the next one go from 0 to 1, and the next one from 1 to 2, and so forth. Okay? And remember, the goal is to find the area under this parabola from x equals -1 to x equals 4, or rather between the parabola and the x-axis. Okay. So what we're going to do to start with is we're going to draw a rectangle where the height of the rectangle is the y value at -1. And we're going to draw that rectangle all the way through the first subinterval. Okay. Now the height comes from the left side of that interval. The height comes from the left side, so this is called a left sum. If we did the next one, the y value at 0 is 0, so we just draw a line segment there. Okay, so there's another left. And so we just kind of continue on with this idea using the left side of each subinterval. Find the y value at that place, use that as the height of our rectangle, and then the length of the subinterval is the base length of the rectangle. And so I'm going to continue to draw these and calculate these areas just kind of visually. Now the last left endpoint of a subinterval is actually at 3. Even though the entire interval ends at 4, I don't use this one, right? Because if I use this y value, then that would go into the next rectangle, which is outside the interval, right? All right. So what we're essentially doing is we're doing base times height, base times height, base times height. There are 1, 2, 3, 4, 5 rectangles because that's the number of subintervals I have, right? Okay, so the left sum would be, let's see, the height there is 1 and the base length is 1. Now, this is not drawn to scale. This is actually a square, but I've condensed the graph some so that you can see more of it. But the height is 1 and the base is 1, right? So we have 1 times 1. And then we have to add 0 times 1, and then we have to add 1 times 1 again. And then we have to, okay, this height is 4, so that would be 4 times 1. And then we could do, let's see, 9 times 1. Okay. Okay, so that would add up to what? 1, 0, 1, 4, and 9, which turns out to be 15. Okay, so the left sum would be 15 for this area. Now, what's really happening, let me replace some of these numbers with some generic ideas, okay? So the first thing is actually f of negative 1, right? The first thing that I did there is I found f of negative 1, right? I found the height of this rectangle is the y value when x is negative 1, okay? And so on, right? So the next thing is f of 0, and so on, right? And let me replace all of them so you can see what's going on. 1, 2, and 3. And remember, we're not using 4 because this is a left sum. So I've used 1, 2, 3, 4, 5 left-hand numbers, left endpoints of each subinterval to be exact. Okay. Now, 1 is the length of the subinterval. So this is kind of our delta x, okay? And this is our f of x sub I, okay? So each I index is telling us, well, this would be our first, second, third, or 0th. I think if you started at the left endpoint, this would be x subscript 0, x1, x2, x3, and x4, right? And then if we did this with a right sum, you'd be using the other numbers, right? So let me go ahead and put those up in a different color, and we'll find those out. And we'll see what the right sum looks like. So in this case, we're going to use the right-hand 5 numbers rather than the left-hand ones, right? So let me erase a couple of things here and figure out what the right sum would be. And I'll put that up, in a different color, maybe black or something. Up here, the right sum for this function would be something, right? And so what that would be is I would use this point as the height of the first rectangle, but then I want to only use the right-hand side of this first subinterval as the height. So then this would be the next one, and this would be the next one, and you can see that these rectangles are going to be bigger than the area that I want. But the other rectangles, the blue ones, are less. So one is an overestimate and the other one's an underestimate. But this is a right endpoint, this is a right endpoint, this is a right endpoint, this is a right endpoint. And so if we added all these up, we would be doing, this would be f of 0 to start with, and then f of 1, and then f of 2, and then f of 3, and then f of 4, right? And what that turns out to be equal to is 0 times 1, so that would be 0. I'm not sure why my pen's not working, but that's supposed to say 0. 1 times 1, which is 1. 1 times 4, which is 4. And then 1 times 9 would be our next rectangle, and then 1 times 16. So our right sum is, I guess, 30, maybe, if I did my math right. Yeah, 25 and 5 is 30. So you would think that the actual area is somewhere between these two, right? And you would be correct, but it's not the splitting the difference, right? So if you added these and divided by 2, you get 22.5, and that's not the actual answer. What happens is, if you let me get the pink color out, if you split the difference, then what's happening is you're finding these areas. So this would be like a triangle, and this would be a triangle. This is not covered in the Calculus 1 book that we use at Johnston Community College from NC State, but it's called the trapezoid sum. So because these polygons that I'm drawing in pink aren't rectangles, they're trapezoids, and you can see that this is a very good approximation of what the area is, right? Okay, so that's what happens if you average these. You get 22.5. Excuse me. All right. There is another way of approximating this area, and it's called the midpoint sum. Let me just erase all this. So the midpoint sum, what it would do is it takes the middle number, so say negative 0.5, finds the y value at the midpoint of the subinterval and uses that as the height of our first rectangle. And the reason why people think this is a good idea is because you can see that part of the rectangle is below the curve, part of the rectangle underestimates the area, but then the other part overestimates it. These two don't really cancel each other out, but the idea is that this is better than just left-hand or right-hand rectangles. Okay, so at 1.5, if you square that, I think you get 2.25 and so on. And I'll just quickly draw these so you can see them, and then I'll calculate their areas. And you'll see that this is not actually the same thing as the average of the left and the right-hand rectangles. Let's see, 3.5 looks like it's about right there. Okay, so what happens if we add these pink rectangles together, right? So this is called a midpoint sum, and we would do f of the midpoint of the first rectangle. Actually, it's negative 0.5, right here, and then this midpoint, and then this midpoint, and so on, right? And there'd be 5 midpoints. So we won't go all the way to the left to calculate our area. We won't go all the way to the right to calculate our area. We stop halfway between the left and right endpoint of each subinterval. Okay, so we do f of 0.5 times the base length of that rectangle, which I chose to be 1. That would be negative 0.5. Sorry, this is 0.5 times 1, and so forth, right? All the way until I get all of them. There should be 5. Okay, so if we add all this up, we get a sum, right? And let's see, this turns out to be 0.5 squared is 0.25. So this is also 0.25. 1.5 squared is 2.25. This is 6.25, and this is 12.25. So if you add this up, this is 5 quarters, which is $1.25. And then let's see, 3 and 6 is 9, and 2 is 11. So 21.25, right? 21.25. So we have 4 like representations of what we think the area is, and none of them are actually exactly correct, right? None of them are. And you might be wondering, well, how do we do a better job of getting that area? Well, one thing you can do is you can draw more rectangles, right? So you can imagine, let me just do part of this, you could do left-hand rectangles that are really skinny. And this does a better job, right? And I'm not doing the greatest job with my artwork, but hopefully you get the idea that you can, you can do a better job by squeezing more rectangles in there. And what happens is this length, this delta x, is getting smaller, right? So what's happening is the limit of this, as this approaches 0, then these rectangles get super thin, almost like line segments, if you will. And then there are more and more and more rectangles, right? Okay. So as a Riemann sum, what we could do is we could either use the left or the right or the midpoint rectangles. But the area of the actual area, the exact area, would be the sum of a bunch of rectangles, right? From I equals 1 to who knows how many, right? Then you'd have to find f of each x subscript I, whether it's left, right, or midpoint, and then do delta x, which is, okay, so this is the height of the rectangle, this is the base of the rectangle. This is one rectangle at x subscript I, like maybe this one, right? And then the summation from the first rectangle to however many there are, okay, adds them all together. Now, if there's a finite number of rectangles, we're not going to get the exact area. So what we have to do is we have to do the limit of this sum as delta x approaches 0. And what happens as delta x approaches 0 is the number of rectangles goes to infinity. Wow, right? There's a number, it's an infinite sum, right? So that's kind of what a Riemann sum is. And so for the area for this parabola, right, okay, you would evaluate these from x equals -1 to 4, right, and your x subscript I would be evaluated by squaring it, right? So that is your Riemann sum from I equals 1 to whatever, and then you have to find your limit delta x approaches 0. Now, some books will call this an n for n rectangles, but there can't be n rectangles if this approaches 0, right? There's going to be so many rectangles that you can't add them all together by hand, so you have to evaluate a sum. And evaluating that sum is very difficult. You can look in a textbook. If you're one of my students, you can look at your NC State textbook and see how they do that for certain functions. And I can add some more resources in the comment section. If you comment and ask, I'll give you some resources on how the Riemann sum is evaluated algebraically. It's kind of a pain, and I don't have time to cover that in this video, but that is pretty much a rundown of how to do left, right, midpoint sums for a certain function and what a Riemann sum is. Okay. Now, I will say that when we are doing these rectangles, sometimes the graph can go below the x-axis, like this one, right? This is the reason why I put this function here. So what would happen if, let's say, we use 3 rectangles, right, from -1 to 0, 0 to 1, 1 to 2, to find the area between this graph and the x-axis? Well, what would happen is our first rectangle would be, here would be your f of -1, and it would look like this. It would be below the x-axis, right? And you can see that in this function, if you evaluate that at -1, that is negative, right? So your height of your rectangle is negative and your base length is positive, right? So this area below the x-axis, the actual area of that rectangle is positive, okay? But when we take what's called the integral counts this as negative. Okay, and so what we call that in calculus is we call this the signed area. Okay, So this would be -1. It's not actually an area of -1. The area of that rectangle is +1. But we're counting it as negative because the area is below the x-axis. So any areas that are above, like say this one, that would be counted as +1, right? Okay, and then you would think, well, -1 plus 0 plus 1, the left sum for this would be 0, right? And that's not true because there'd have to be an equal amount of area under the curve above the x-axis and below the x-axis, and that's not happening, right? So the actual area below here would be this, and the actual area above would be way more than that, right? Okay, so let me explain how you can write this area as not just a Riemann sum, but this thing that we call an integral, okay? So the area between this graph and the x-axis, the area between x cubed and the x-axis, and what we mean by area is the signed area, okay, where some of the area can be counted as negative, would be written as this thing called an integral. And remember, we've seen this in prior videos, right? So there's this long letter S from Old English, and then you would take your function, which is counted as the height of each rectangle, and then dx, which is part of the derivative dy dx. This part by itself is called a differential. So we have our function, and we have what used to be delta x is now called dx, and then this integral is actually the limit of the sum, right? That's why they use this capital letter S here for integral, okay? So it's the limit of the sum of products of heights and bases of rectangles. So that's what that is. And if you want to count area, then you start your integral at the lower end point of your interval, and then you do the upper end point of the interval. So this expression that I've written here is called a definite integral. Definite integral because it has numbers on it. And the definite integral is written like this. It has an integral symbol, it has a lower limit and an upper limit. It has the function, which counts as the height, the y values, and then the dx, which counts as the x values. So you're multiplying x times y, x times y, x times y, and you're adding it all together and taking the limit of that sum from somewhere to somewhere else, right? And so this actual area minus this actual area is equal to this integral. Okay. Now, my students that are using Maple, you can actually use Maple to evaluate this integral, but I'm going to show you how to do it without Maple in just a moment. Okay, so that is what a definite integral is, and we are going to understand that as what we call a signed area. So go back and watch that again. I encourage you, if you're one of my students, to read the textbook that talks a little bit more about this in detail. Okay, now before we get to how to evaluate that integral without Maple or without some technology, I'll show you how to get the exact answer. Pretty easy actually. We need to talk about this thing called an indefinite integral, and remember in last week's videos there's this thing called an antiderivative, right? So I'm going to ask you, what is an antiderivative of x cubed? Think about what function's derivative is x cubed. So see if you can work backwards. Pause this video for a moment and see if you can work backwards and figure out what that would be. Okay, so you're back. I have a reveal for you. So the antiderivative of this is 1/4 x to the 4th, or you could have written x to the 4th divided by 4. And if you did that, sorry, I meant to erase there, my bad. Let me show you why that works. And you might have put a number added to this, and which is fine too. But if you did 1/4 x to the fourth, then what happens is the derivative dy dx is 1/4 times 4x cubed, right? And then these 4's cancel out, and there you go. So what I'm going to show you right now is what's called the power rule for an antiderivative. And by the way, we'll talk about the fact that you could have gotten another different answer, like 1/4 x to the fourth plus 17 would have worked, right? All right, so if f of x is x to the n, right? Remember that the derivative, which is, I'm going to kind of go to the left here, the derivative, what we do is we move the power down, multiply as a coefficient, multiply the coefficient by the power, and then reduce the power by 1. Okay, that was the power rule for derivative. Okay, so if we move forward this way and we do this capital letter F, you remember that from the previous video, that's the antiderivative. We're going to do the exact inverse of those two things. So instead of multiplying and subtracting from the exponent, we're going to add 1 to the exponent, and instead of multiplying, we're going to divide by that new exponent. Let me say that again. Instead of multiplying and subtracting, we're adding and dividing. And since you added first before dividing, this is not divided by n, this is divided by n plus 1, right? So if your function that you're given is x cubed, then your antiderivative is x to the fourth divided by 4. Now, if I attach a word here, I'm going to say general antiderivative. You can put plus any constant here. You can add any number you want. C stands for constant. So, let's say that we had y is equal to x to the fourth divided by 4 plus 231.5, right? The derivative of a constant is 0, right? So, let's see, the derivative would be 4x to the third divided by 4 plus 0, and we know that that's x cubed. So, if the derivative of this function is x cubed, then the antiderivative of this function could be this thing, right? But instead of writing down a whole bunch of different bogus numbers, we just call it a general antiderivative by adding a c. Okay? So what does that have to do with an indefinite integral? That's a good question. I'm glad you asked. The indefinite integral of x cubed with respect to x is exactly the general antiderivative. You would say that this is x to the fourth divided by 4 plus an arbitrary constant. So an indefinite integral uses the antiderivative, but it uses the general antiderivative. So for example, if you had, say you wanted to do the indefinite integral of x to the fourth plus 2x squared plus 1 divided by x, okay, we could use the power rule to do this with one exception, and I'm going to leave this undone for a moment. And there's a reason why I'm going to leave it undone for a moment. What happens if we are going to do x to the negative 1? Watch what happens. If you use this rule, you would increase your exponent by 1 and then you divide by 0. Whoa! This is no bueno. You can't divide by 0, right? So the rule doesn't work when the power is negative 1. There is a special case here when the rule is when your exponent is negative 1, or in fact, if you just want to write this as 1 over x, the antiderivative we now know is the natural log of x plus c. And the reason for this is because the derivative of the natural log is 1 over x. Now, for reasons I don't want to explain in this video just yet, I want to make sure that you understand that since x could be negative on the function's graph, you can't have a negative x value in a logarithm, so what we do instead is we take the absolute value of x. Okay, so now the domain of the original function and the domain of the antiderivative are exactly the same. This is defined everywhere except at x equals 0. This is defined everywhere except at x equals 0. Okay, so the reason why I told you that, this is a special case when n equals -1, okay? The reason I told you that is because it's going to come up here. What I would do to evaluate this integral is I would divide everything by x. So there's, by the way, there's no quotient rule for integrals. There is no quotient rule. There is no quotient rule. Don't try to do it. It's not there. Okay? What we're going to do instead is divide each one of these things by x. So we're going to do x to the third plus 2x plus 1 over x. You can write that as x to the -1 if you want. And all this is multiplied by our differential dx. So now we don't need to write this integral sign anymore. We're going to evaluate this integral by writing its general antiderivative. So this is x to the 4th over 4 plus 2. Now, what's the antiderivative of x? Well, if x to the 1, we'd use x squared over 2, right? The constant stays put, just like it did in derivatives. And then we'd have the natural log of the absolute value of x plus an arbitrary constant. And of course the 2's can cancel out here. So there you go. All right. Now you can check your answer by finding the derivative of it, right? So if the derivative of your answer is not what's behind the integral sign, then you messed it up. Okay. Another thing, I know I'm sending out a lot of information, and I told you guys this is a tough class. I get it. Let's just go back and remember some vocabulary. So this is called a differential. In future classes, this could be d theta, dt, dy, d whatever variable, right? The function that you're integrating is called an integrand. The integrand. And in this, of course, is called the integral sign. This is the integral operator. All right, so we're saying the integral of x cubed with respect to x. Sound familiar? Just like when we did dy dx, how did we say that? The derivative of y with respect to x. That's how you read it. Okay. All right. Now, I promised you something earlier in the video. So the grand finale of our video is how the heck do we find this area? How do we find this exact area? This area, I guess, subtracted from this upper area. So what's the difference between the area above the x-axis here and the area below the x-axis? I'm going to show you how to do it. The exact area is found by evaluating your indefinite integral at the endpoints. So let me show you how this works. And it's called the fundamental theorem of calculus, and I'll show you what that is in a minute. But we're going to find our general antiderivative, and we don't need to write plus c, and I'll explain why in a moment. But we're going to evaluate this from x equals -1 to x equals 2. You put the 2 in first, and then you put the -1 in. Okay, so you do that, you get 16 divided by 4 minus, what's that, 1/4. So this is 15 over 4. And that's the exact amount of area here. Subtract this amount of area here. Exactly. Perfectly correct answer, right? Okay, so how does that work out? What the heck is this fundamental theorem of calculus? So this is the way that it reads. If you take a definite integral of any function with respect to x from x equals a to x equals b, then This is the antiderivative without the plus c on it, okay, evaluated between first at x equals b, then at x equals a. So this would be capital F of b minus capital F of a, where capital F prime of x is exactly equal to the function that you're integrating. Okay? Now, you might be wondering why I didn't write plus c. Well, if you did f of b plus c minus f of a plus c, the plus c's would cancel out. They'd subtract out. So it's kind of a waste of time to write the plus c for a definite integral. But here, you need to write the plus c. Okay? General antiderivative has to have it. Okay? So definitely write this down. This is the fundamental theorem of calculus, and it is super important. It is something that we are going to use quite frequently throughout the remainder of Calculus 1 and oftentimes into Calculus 2 and 3. Okay, so go back to where that was in the video a few seconds ago if you need to write it down. All right, so what about this other one? Remember what we started out with? Like, what was that area, right? How much area is there exactly in this region? And I did a horrible job there, but anyway, you get the idea. Like, how much area is there in all this stuff? Okay, so how do we do that? We would do the integral from -1 to 4 of x squared with respect to x. We evaluate our antiderivative. Remember, I add 1 to the exponent and then divide. From x equals -1 to x equals 4. I put the 4 in first. I put the -1 in second. And I subtract the results. So this would be 64 over 3 minus, this is -1 over 3. And in subtracting a negative, I get a positive. So the answer is exactly 65 over 3. Or I think that is 21 2/3. So remember our left-hand sum and our right-hand sum. The left-hand sum was 50, right-hand sum was 30. The average was 22.5. And I don't remember what the midpoint sum was. I think it was 21.25, if I remember correct, or maybe 22.25. You'll have to go back earlier in the video to see if I'm right. I don't remember that number, but in any event, this is the exact area. This is the exact answer, okay, without having to do midpoint left or right hand approximations. Okay, and it uses this beautiful result called the fundamental theorem of calculus. So that's all we have time for this week. I know that was a lot of information. Go back and read through it slowly. Take these in bite-sized chunks when I go through the different parts, and reach out to me if you need help. Leave me a comment. I'd be happy to answer questions and comments on YouTube or through my email if you're one of my students. So until next week, have a good one.